In our problem statement, we're told that we found a small animal 12 inches in height that's present in the area where we have our project. And so we need to redesign our roadway so drivers can stop if they see this animal in the roadway. So we're specifically, in this example, being asked to find the new length of the vertical curve for this current curve with a PVI of 11 plus 70 to meet this new requirement. So looking at this curve a little more closely, we've got our PVI that's at this point. It has a station of 11 plus 70. The elevation of that PVI is 171.12 feet, and it's a vertical curve with a length of 140 feet. So it means going from the PVC to the PVT is 140 feet, and has a K value of 29. The K value is the rate of vertical curvature. This corresponds to needing to go 29 feet to have a 1% change in grade. So this is the curve we're looking at. We have a entrance grade G1, exit grade G2. That G1 entrance grade is 4.5154%. The exit grade G2 is negative 0.3%. That gives us an algebraic difference in grade when we take the difference between those two grades of 4.8154. And if we go back to our K value, that rate of vertical curvature, that corresponds to a design speed of 35 miles per hour. When we go to the AASHTO Greenbook, look for a crest vertical curve, because our shape of this curve is a crest shape, and it's a vertical curve. So that 29 corresponds to 35 miles per hour design speed, and we'll see that come up when we get into the details of solving this problem as well. So there's two equations we're going to use. Both these come from the AASHTO Greenbook, page 3, 166. There's two scenarios we may have. So the first scenario is when the sight distance is less than the length of the curve. The second equation is when the sight distance is greater than the length of the curve. Now, from the beginning, we don't know exactly what situation will apply, so we have to sometimes calculate both. If the first step is correct, the first equation you use is correct, then you don't need to move to the second one. But one thing we should have in mind as we're working this problem, the current curve has a length of 140 feet. If we're going to move that height of the object from 2 feet, which is the default, to 1 foot, which we're being asked in this problem, we know we're going to need a longer curve. So just before we actually start these calculations, we should have in our mind that we're looking for a value for the length of the curve that's longer than 140 feet. The variables in these equations that we're going to use, we have our length of vertical curve, L, in feet. This is what we're solving for. The algebraic difference in grades that we solved on the previous slide is 4.8154. The sight distance, S, is 250 feet, and that also comes from the AASHTO Greenbook, page 3, 170, using that design speed of 35 miles per hour. H1 is the height of the driver's eye above the roadway surface. We're not told that we need to modify that for this problem, so we're going to use that default assumption from AASHTO of 3.5 feet. And our H2, the height of the object above the roadway surface, this is what we're modifying. This is why we have to use those default equations. We have to use the base equations instead of the default values in the Greenbook. 1 foot for our height of the object instead of 2 feet, which is the base assumption in the Greenbook. What will typically happen if you're using the default assumptions, our equation for the length of the vertical curve is simply L equals K times A. So everything outside the A in these equations is what builds up our K value that we're going to have for this curve was 29 when we kept all those default assumptions in place. We're now modifying those default assumptions, in particular H2, using 1 foot instead of 2 feet there. So let's start plugging in the values into these equations that we have. Using the first equation, in the scenario where S is less than L, we get an L value, the length of curve of 183.95 feet. Well, this is actually less than our sight distance of 250 feet, so that equation is not going to work, which therefore means the second equation must be the equation that we actually need to solve this problem. Putting in our values of S, A, and H1 and H2, we find an answer of 157.7 feet. That is less than our sight distance of 250 feet, so that's the correct value. Thinking back to our original curve length of 140 feet, it is also greater than 140, so this value seems like a reasonable and practical value when we adjust that H2, the height of the object, from 2 feet down to 1 foot.